All right, friends, we are going to talk about the third type of motion, of projectile motion here. This is where we are launching or throwing an object from the ground at an angle, and it's coming back to the same height. So this would be like kicking a soccer ball, a football, something that goes up and comes back down right to where we started. Okay, this is going to mirror the type 2 problem when we think about the initial velocities. We still have to use trig to break it down into the x component of the velocity and the initial y component of the velocity. And so those pieces we know right away once we do a little bit of trig. Some other knowns that we can deduce from the problem. This is just like when I was throwing a ball up and it was coming back into my hand. We know a couple of things. We know that the height that it travels, excuse me, is, when we think about it in terms of a displacement, is going to be 0 because it does not change position if I'm considering a final and an initial. It's right back in my hand. The difference, though, is that in the x direction, it will, of course, change a position. It will get further from where I launched it. It's just going to come back to the same height from which I launched it. So my displacement in the y direction will be 0. Just like when we threw something up and it came back to my hand without an x component of this, we know that the initial y velocity is going to be equal to, but opposite, our final y velocity. And so when I break that down using trig, I know what it's going to be at the end, which is really nice because I'm going to walk away from this problem knowing 4 things before I even start an equation. Because the last thing, of course, is acceleration due to gravity, which is 9.8 meters per second in this case when we're on Earth. So let's try it out. Beep, 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 beep. Let's find it. Sorry, this is the second one we just did. Here we go. Beach ball is thrown with a velocity of 3.9 meters per second at an angle of 35 degrees from the ground. What is the horizontal range? How far did it go in the x direction? So we have to start first with our vector. We have a value of 39 meters per second at an angle of 35 degrees from the ground. So I'm going to do some trig. I'm going to draw in my x component and my initial y component here. I know this is going to be cosine because this is the adjacent leg and this is the opposite leg. This isn't always the case. X is not always cosine, but in this case it is. So cosine of theta is equal to adjacent over hypotenuse. I write this every time so that I do not make an error because this is where the error is going to be. And if that's the case, you're going to carry that error through the entire problem, and that would just be absolutely terrible. So I'm going to plug in, I'm going to do some math, and I end up with 3.9 cosine of 35. I'll do the math in a second. Y, I'm going to use sine of theta is opposite over hypotenuse. You guys are going to get really good at this if you don't already feel like you are. 3.9, do some math. Sine of 35. So 3.9 cosine of 35 is 3.2 meters per second. So a lot of this vector is going in the x direction. And 3.9 sine of 35 is 2.2. So just a little bit in the y direction. Okay, sorry, that you can't see yet. Oh, I forgot I can make this bigger. Let me make it bigger for us. Okay, so now we're going to separate our page into x and y. We're going to list what variables do we have to keep track of. This really is just organization, but it lets us know what to do next. Okay, so some things we know. We know our velocity in the x direction is 3.2 meters per second. We know our initial y velocity is 2.2, and it's going upward. So let's talk reference frame for a second. I'm going to say down and left is negative, and so that means my initial y velocity is going to be positive. Some other things I know, I'm throwing it from the ground, it's returning to the ground, and so my displacement in the y direction is 0. My initial height minus my final height is 0. And then I also know acceleration is down 9.8 meters per second squared. According to my reference frame, it's going to be negative. There's one more piece that I do know. I don't necessarily need it for this problem, but it might help in selecting an easier equation. Because I'm throwing it up at 2.2 and acceleration due to gravity is acting at a constant rate, it's going to be coming down right before it hits the ground at that same velocity, 2.2 meters per second. I just know it's going to be down, so it's going to be negative. So I have to solve for a time. That's nice because it saves me some time solving. Now I can use this equation because I know my final velocity, I know my initial velocity, I know my acceleration, and so I can solve for time. Reference frame is going to be key here, negative 9.8t, so I have a negative 2.2 is equal to a positive 2.2 plus a negative 9.8t. I'm going to subtract 2.2 from each side to get a negative 4.4t. So it's clearly not in the air very long. I'm going to take 4.4 divided by 9.8. And I get a time of 0.45 seconds. That's pretty fast. That means over here, 0.45 seconds is the only time it's in the air. I know displacement is equal to a velocity times time. Did you see how I skipped that first solving step? That's fine. I'm still starting with an equation in variable form. And I end up with 3.2 times 0.45. I get a displacement of 1.4 meters. Not very far, but I'm not launching it very fast. So that's how you solve projectile motion problems. Now you go try it.